Good afternoon, everybody. My name is Nicolo Cairo, Project Officer at ETN Global. On today, 29th of September, we are going to start a new webinar series by ETN Global. As you can imagine, this is a rather new initiative that we are carrying out for our members and also the external who are interested in understanding the economics of the thermal assets. It is something new, as in the past we rather touch upon more technical topics, but today in this first kickoff webinar of this series, we will discover the basics, fundamental for the economics with Stefano Mazzoni from University of Rome, and with Engie, hereby represented by Armando Salas and Xavier Degive. I hope I pronounce your names correctly. And in this webinar, you will have two presentations, indeed of 30 minutes each one followed by a question and answers session, ultimately also followed by a Slido, so a questionnaire to review the quality of our webinars. You are now muted and you will not be able to turn on your camera during the presentations of University of Rome and Engie. However, you will be allowed to do so during the question and answers. With this in mind, I propose we start with the presentations, and I will give the floor to my connational from University of Roma, Stefano Mazzoni. Please, Stefano, the floor is yours.
Yeah, thank you very much. Good afternoon, everyone. Thank you, ETN. Thank you, Nicolo, for the kind introduction. And I'm a professor in the University of Rome, and I'm going now to share the content of the presentation. And please let me know if you can see the PowerPoint. You see an Excel below because I'm going to show you a practical case on how to compute some of the matrix that we are going to present in the presentation. And let me know if everything is clear. So I will start with the presentation itself.
I can see it.
Good. So brief background, I am working on energy conversion system since 2010. I've been working under University of Rome 3 during the first decade of the 2000 in a couple of European projects coordinated by ETN. I was working on large CCGT power plant, then concentrated power plant with gas turbine. And then I moved to Singapore, where I've been working on optimization of multi-energy system. And there in Singapore, I've got some expertise on business related to integration of key financial indicators to carry out techno-economical environmental assessment. And that's why together with ETN, today we are planning to show you which is the methodological approach to try to be as much comprehensive as possible in evaluating the key economic and environmental metrics for power plants in the near terms. So, first of all, of course, all of us know that there is capital expenditure, operating expenditure, and revenues. But what we need to understand is that these key indicators need to be linked to the specific context we are positioning our business. So the combination of these three metrics allows to identify which are the net present value, levelized cost of electricity, or someone called levelized cost of energy, and the return on investment. Plus, there are other terms related more to financial indicators, such as like the internal rate of return. And these three metrics allows to understand how to position the power plant and the business line we want in the market that we are dealing with. So today we are going to understand which are the main terms that characterize the fundamental economic of the power plants. We will start with the CapEx, in which we understand which are the terms that are mainly used for computed the CapEx with the proposed methodology that many times people ask you is how to compute if I don't have a reference value. a classification of the operating cost ranging from the fixed one to the variable one, and then we separate fuel and cost and CO2 because these one are the one required to run in the plant itself. Then a structure of the new revenue model scheme that up to date are taking into consideration, since each power plant could be beneficial for supporting also ancillary services, not only just electricity generation. Then I will drive you through the calculation of net present value and LCOE. And then I will show you a practical case studies on Excel, where I will change some sensitive parameter to show you which is the effect on the two key index like NPV and LCOE. And I will show you a couple of case studies that have been carried out when I was living in Southeast Asia. So I think that it's important to understand that capital costs are typically independent from the time of the operations, except of extraordinary capex may be related to replacement, but we will drive you through that later. While operating expenditure are part of them fixed and part of them dependent on the time. So in the understanding of how the money should be dispensed when you build a new power plant, you need to account for something that is a fixed cost and something that is time-dependent cost. And on this basis, basically also revenues become directly only on time operational, because if the system doesn't work, there is no revenue. There is a small part of the revenue that takes place as a constant cost at the end of the lifetime of the plant, that is the disposal cost, but this is really a small amount. And all these three indexes are important for identifying the financial indicators. And in these metrics, these four boxes that you see are all important in the way that you understand the appraisal of a technology. So if you need to go for a CCGT or for an open cycle gas turbine, whatever is the layout, you can compare the viability by just comparing these three metrics like CAPEX, OPEX, and revenue, and then combining them into the financial indicator. You can benchmark and compare the different projects in respect of the reference one you would like to benchmark. So let's start with capital cost. So capital cost covers all the upfront cost, and they will range between site acquisition and preparation, all the EPC, that is engineering, procurement, and consumption, all the plant equipment and installation. I highlighted them because later we will make a small breakdown on how to compute this part of the CAPEX, the grid interconnection infrastructure, the contingency, and the financing. So you can see that CAPEX is a general term, that is capital expenditure, but it accounts different part of the plant. Something that I haven't put inside because it's indirectly connected to the financing cost. There is also the part related to the risk assessment and the fact that an optimized design with lower CAPEX also reduce the premium, for instance, of reinsurance to purchase the coverage of the plant. So basically all the CAPEX, the overall amount, can be computed like the sum of all the terms that we would like to compute of a reference value for each of the components and of each type of all the voices inside this type of cost. So basically it's a double summatory. And just as an example, when you're dealing with open cycle gas turbine, you need to account for compressor, burners, expanders, some auxiliaries. While when you're dealing with a CCGT, you need to account also all the heat exchanger devices that made the heat recovery steam generator, the condenser, and higher electric integration, all the auxiliaries like pumps, additional filtering, the mister, and so on. So how do we compute this term, the plant equipment? Basically, you need to enter the details of the power plants, understanding which are the main components that constitute the plant, and start to identify which are the ones that compute actually the cost, because usually you have what is called balance of plant, BOP, that is a percentage of the investment cost for the plant equipment, that are the small costs such valves, small piping, sensors that are not computed directly, While for the main components, such as the gas turbine, the heat recovery steam generator, the steam turbine, the condenser, the filtering, and the pumps, usually you compute the capex for each of the components. And of course, as mentioned before, for the CGT, you can also break it down in compressor, burner, and expander, and so on. But let's say that for this approach, now we will consider the cost of the technology, so a gas turbine. The point is that when you are asking for quotation, typically the OEM are not so open to disclose the prices and the cost of each technology. So sometimes if you're rushing and you need a bit of support of some numbers for evaluating the feasibility of the project before the OEM reply your email asking how much is it, how you can discount it, and so on, you can consider to use an approach that is called factorized methods. This is a modified formulation that we publish with some of my researchers in some publication, but the concept behind this is that you have a reference cost related to a reference capacity or a reference nominal condition of the system, and you can compute the actual cost, that in this case I call target capacity, target cost, sorry, in respect of a target capacity on the power on n, with n that typically ranges between half and 85. And then you can correct it with some parameters that take into account the inflation, the currency, the location, the geolocalization, some additional regulation to account for. And then there is a multiplication of different factors that typically correct it. So if I buy a pump that should be working at ambient condition or a pump that works in cryogenic or high temperature condition, you use this formula and then you multiply by a correcting factor that can be greater or minor than 1. And so basically, this is a traditional approach that allows to have a good compromise between accuracy and cost evaluation that can start to give you an identification of which is the magnitude of the capital cost that you want to invest for starting the business. So you typically the shape of the curve is something along this polynomial expression in which you have a nominal capacity or a normalized capacity respect the cost, and then you can identify where you are, and after the identification of your point, you can correct by the factors. Here I show how, for instance, this methodology can be adopted. Basically, I went to an IEA report, I think, of 2021, in which there are some costs related to CCGT and OCGT power plants in different countries for different capacity. So clearly, if we want to install a capacity in a region that is close by one of the one listed here, but I don't have the net capacity that is perfectly matching this database, let's say, I don't know, we have 450, we will be entering the formula with 500 as reference cost, the cost per kilowatt expressed in US dollar per kilowatt electric at 1,000, for instance, and then we will, sorry, 1,000, for instance, and then we will correct with the rules of the N here, the ratio between 450 over 500, 1,000 divided the unknown variable, and then we can compute by fixing the index N, which is the cost of a just slightly smaller project. So basically, if it's 450 instead of 500, if this one would have been linear, we would have considered basically a 10% discount, but clearly it's not because there is a correction that goes with the power of n. So instead of 1,000, and it would have been 900, probably would be something around 925, 930. And this methodology can be easily scaled up to all the components. Here, there are the terms on the investment cost, is what I mentioned here with the index here, where you have a reference project with a certain inflation rate. If you move the project to another country, you just correct the inflation rate in respect of the other indexes. Now we go to the second part, that is the most interesting to my perspective, that is the one related to the operational cost. So in this section, we will distinguish mainly three voices for the cost. One is the fixed OEM, one is the variable OEM, and then the other one that is related to the fuel cost, and I added also CO2, because in this energy transition, we would never forget that in many countries in Europe, we have to pay high carbon tax. So basically, this is something that we should consider. So basically, when we start to look at this breakdown of the operating cost, basically we have some cost that doesn't vary together with the output of our power plant. So despite I run the plant or I don't run it, once I build it up and it's on operation, I need to pay the staff salary, some insurance premiums, the administrative overhead, the maintenance. Sorry, there is a typo 2 times. And this one typically is computed as a percentage of the capex. So basically, you have all these terms. The operational cost of the FAM can be calculated like a fixed terms of the capex, and each voices as a percentage in respect of the capex. So by summing them, you can establish what are the fixed OEM. Then we go to the variable one, that are the one that take into account the scalability of the production. So I run the plant longer hour in a year, this cost increase. And this one account for the not predicted maintenance, so the unscheduled one, some consumable, and wear and tear replacement. And this one typically, instead of being expressed as a percentage of capex, they're expressed as cost per megawatt hour generated. And indeed, they are, that's why I put the integral to show that there is a time dependence of them. So basically, it's the power output by the time, so basically the electricity generated, by the fixed cost, by the fraction of each voice, and by the cost of each voice. And then we go to what is the plant operating. That basically, this one depends also on the optimal dispatch strategy that you use for running the system. So this one basically can be adjusted for accounting different heat rates. They can include the carbon cost, and they can be adjusted in respect of the power plant efficiency. And basically, these ones are the one that depends on the price variability and the dispatching. So basically, you have the operating cost for the fuel. I have computed here the power plant divided by the low heating value and the efficiency of the plant give you the amount of fuel that the energy introduced as heat by the fuel into the system, by a cost of the fuel over the time. And then you have the operating cost related to the carbon emission that I didn't put the carbon tax on purpose here, that basically is related to how much CO2 you produce over the year. And so basically, for summing up onto the operating cost structure, you have a fixed part that basically is capex proportional that you can compute at the beginning of the feasibility study of the plant, and then a part that is time dependent. So you have the variable cost, fuel cost, and operating cost related to carbon tax. And that basically depends on the optimal dispatching strategy, because you can decide how to operate and in which condition, especially when the plant is integrated in a highly interconnected grid. Now we pass to the revenue modeling, and this is something that probably is changing a bit in respect of the past, because now we have multi terms that can compute the revenue. So if before the only revenue that you could have considered was the production of the kilowatt hour to be sold to the national grid, plus some additional service like the spinning reserve, the primary and secondary reserve, now you have multi-service that you can include into the revenue model. And it is something that we have been discussing already in last meeting in BEG, and we have been continuing on this topic. It's something that we should really consider in the way that we are approaching the new way of managing large CCGT power plants, because actually the operating hour, and we will see later the example, the capacity factor affects very much the economic viability of the solution. And when you can start to think of different revenue model, you not only increase the profitability of the asset, but you can consider also to operate longer hour over the year the asset. And so in the revenue model also I fix the traditional one, that is the integral value of the electricity generated by the price that you sell the electricity you generated, plus the sum of many terms. This is a Dirac delta that can be 1, 0, so it's a binary variables that activate or deactivate the temps. And you can consider like ancillary service like the frequency regulation, operating reserve, voltage support, black start capability. Then you can go to the capacity market, or maybe some additional consideration on how you can take into consideration bioproduct to be sold, like cogeneration plant can sell heat, or you can consider to sell cold. So you can make this formulation as flexible as you like, in respect of the boundary condition you have. Now that we have classified the three terms, CapEx, OpEx, and revenue, we can start to consider which are the financial indicators that typically banks and investors look at. So there is the return of the investment that give you a measure on how much the investment is efficient in respect of the money you invest. The rate of return basically give you which is the percentage that you make a year, explaining you if it's more convenient to invest in this project or in another one. The payback that can be discounted or not discounted represents basically the break-even point between the investment and the cash flow. And then the two ones that we're going to be focused are the net present value that is able to compute which is the value at the money of today of your cash flow between the year zero and the lifetime of the plant, and the levelized cost of electricity or of energy that tells you basically which should be the price of the electricity that you require to be sell the asset you generate for making the net present value zero at the end of the lifetime. Basically, all these indicators collectively can help to be, how to say, informed decision makers in the way that you know really which are the numbers that you need to look at to understand if you go for a project or not. So by combining these five, you have a global picture if and how much is profitable an investment. And also by combining all these five, you can decide where is the profitability coming from. So you want something that gives you a shorter payback, but maybe a lower net present value that anyway make you something positive in short time, or you're looking something that maybe has a longer payback, but with higher net present value. To my experience, nowadays, customers are looking mainly at the shorter possible payback because longer payback means risk. And what I observe in my experience, both from the academic perspective that from the entrepreneurial one, is that at the moment investor doesn't like risk. So they prefer to have something less profitable, but with the shortest payback possible. And by running this analysis with these metrics, you're able to manipulate the variable that intervene into the computation of this asset and understand what is the best solution. So from a mathematical perspective, I just make it short so we can go to the example. The net present value is defined like the investment cost at area zero, that is a negative, so because it's what you pay off at the beginning, plus the sum of the cash flow, where the cash flow are defined like the difference between revenue and OpEx as we defined them in the previous slides, actualized by the discount factor 1 plus E at J, where E is the interest rate and J is the number of years, over the lifetime of the plant. And typically, net present value has this kind of diagram. In academia, we call them like a butterfly diagram because it's looking like two wings of the butterfly that shows the investment, the payback time, and the net present value. When we go instead into the levelized cost of electricity definition, this is basically used to evaluate the specific cost that the plant can generate in certain configuration. And for computing it, the main difference is that we don't account the cash flow directly because the cash flow can be manipulated LCOE by this index and put again on the right term. So in somehow, as I mentioned, is the value that the revenue should have to make the net present zero equals to zero. And so the main difference is that this parameter in respect of the net present value depends on the electricity production per annum that is affected by the capacity factor. So you need to account that a nominal capacity of 300 megawatt running only at 25% of the real hour of the year is less profitable and have a larger LCOE in respect of a power plant that run at 85% of the capacity factor. And this is something very important to understand if the investment is viable, how much you need to sell the electricity you generate, and understand also if by maybe adding a bit small capital investment, I don't know, by buying a bioproduct that can use more electricity to do another low-hanging fruit generation can help in making the LCOE shorter. And this is the typical trend. Of course, the LCOE is asymptotically even usually after the 18, 19 years. So if we would have continued with 25, 30, the value would have remained practically flat. And this one is because there is the 1 plus E at J at the denominator. So this is the trend. Which is the main limitation of the LCOE. The LCOE basically is very good for assessing the impact that fuel capacity factor and discount rates has, because basically in this formulation, in the OPEX and in the electricity, we have the operating costs related to the fuel also. So we define the OPEX, as you remember, as a sum of a fixed part plus a variable one plus the fuel. The capacity factor enter in the electricity generated over the year. But what is not very good, that doesn't really account, is the profit margin and the return requirements, which are the value of dispatchability, and basically is not helping you in identifying how you can changing the financing structure of the project. So it's a very good metrics, let's say, for having a first assessment of where you're positioning the technology you want to install, but become a bit limiting when you want to complicated the revenue model, because as discussed before, in the net present value, you have the revenue as a variable into the expression, in the LCOE is not. So while with the net present value, you can somehow manipulate a bit the expression by considering multiple services that the power plant can generate, with LCOE, you are a bit limited on that. So I don't know if you would like to raise some question before we pass to the Excel file. Nicolo, you can also help me in that.
Yes, Stefano. So I'm going to enable the mics now. So anybody can unmute himself or herself and ask questions to Stefano. You can also raise your hand. Please, Min. You can introduce yourself. You can unmute yourself. Do you hear us?
Hello? Hello? Can you
Hello.
hear me?
Yes. Good afternoon.
Yeah.
Yes.
Sorry. Good afternoon and good evening. Yeah. My question, Professor Mazzoni, could you go back to the slide of the LCOE calculation? Yeah, I just want to ask. You have used the interest rate in the LCOE calculation. My question is why. Normally, the people use discount rate instead of interest rate in the LCOE question, in the LCOE calculation. Could you explain why do you use the interest rate instead of the discount rate or the weighted average cost of capital?
Stefano, I think you're muted.
Ming, thank you very much for your question. Appreciate it. Yeah, you're right. I didn't call it discount factor because the discount factor is automatically including the 1 plus E at the power of J. So I just consider usually the interest rate because in the evaluation, you put in this interest rate, what is the inflation, the deflation of and the interest rate that the money are lended to you by the bank. So we could have also changed the expression instead of 1 plus E at the J with a discount factor, that's it. But in this E, you can put whatever value you want, accounting for inflation, deflation, deviation of the inflation if you want, plus the interest rate of the money.
Pardon, I was muted. We also have a question by Ramon. Please, Ramon, floor is yours.
Yeah,
you can unmute yourself.
Thank you very much. Good afternoon. I have a question. In LCOE formulation, I would like to know why also you correct the energy by the interest rate in the denominator?
Very good question. Thank you so much. So the main point is that this is just a mathematical manipulation. This one is the way that IEA, McKinsey formulate LCOE. Typically, indeed, there is a reference I can share with you later on. But you have to imagine that the discount factor is not really here, but as mentioned before, is to the LCOE. So imagine that if you manipulate this formula, you can imagine that the LCOE goes here with minus LCOE, and here we become 0. So imagine that it's something like that. This one can be 0. And then for doing that, you need to bring this denominator on top. So basically, it's a way to account also for the equivalent revenues, because as we mentioned, the LCOE represents the value for which the net present value becomes 0 at the end of the lifetime. And so basically, if we come back to the formulation of the cash flow is defined as revenue minus OPEX, and basically means that the revenues, the LCOE in this case, are already discounted by the terms sum for J1 end-to-end, 1 plus E at the power of J.
Yeah, thank you. But I would like to mean what is its physical meaning that you correct the energy by the interest rate, because they are not in the same term. Energy in the megawatt hour or something like that, but interest rate is something financial.
Yes. Okay, let's try again I try to express myself differently. So this is a mathematical manipulation of the formula, and this is how it's written in almost all the reference in the world. This doesn't mean that you are discounting the electricity. This part of the terms, if you bring on the left side of the equation, is sum J1 to 1 to n of basically a discount factor that correct the LCOE. So if you have this equation on the left term that goes up on the right term later, you have CAPEX, OPEX minus revenue divided the electricity.
Yeah, I got it. Yeah, great. Thank you very much.
So this one is just the sum here is just to compute the overall work, electric work that the plant generates. And then the sum of it is just to discount this one that is an economic parameter. But usually you represent the LCOE like euro or US dollar by megawatt hour, and this is the typical formulation that you can lump and adopt to compute it in a uniform manner to follow the standards set by IEA, McKinsey, the World Bank.
Yeah, great. Thank you very much.
Pleasure.
Thank you, Stefano. We do not see other questions. I propose you can go ahead with your
Okay, so basically I just prepared a simple Excel file. I will just show you the concept behind. We don't need to run many analysis. So I have split it up as exactly how we build up the presentation. So we have a section. Can you see the Excel? Is it too small? Can you see it?
We can see it.
So basically there is a section with capital investment in which I make an example with this open cycle CCGT or CCGT. There are all the other equipment you can plug it in, plug it out. And then there is a balance of plant that is set as a percentage of the capital cost. Then you have the operating cost evaluation. In this case, later we drive you through, there is fuel, CO2, and maintenance. And then you have the revenue model. And then you have the financial indicators, so the number of years, the interest rate, and if there is a disposal asset value, so the residual value. And the Excel file calculates for you the net present value, and on the other page, linked to this one, the LCOE. So basically, I just created here a mask in which you can change the efficiency of the CCGT. You need to consider that one thing that typically is not disclosed clearly in the report you find in the literature is that even if you install a gas turbine of a nominal efficiency of 38-40%, the value of the efficiency that you need to include here is the yearly average value, because you are running a lumped perform analysis based on the yearly operation. So even if we have a 300 megawatts nominal efficiency 41, I don't believe that we can consider more than 35 as an yearly average efficiency. So this is the yearly average efficiency. I consider an $800 per kilowatt installed capacity machinery at 300 megawatts, so we range to up to 240 million investment. I consider a typical 20% cost for the balance of plant. So we have our total capex. Then we go to the yearly consumption. So basically, I took into consideration the power output generated. So I have computed the power output by the capacity factor divided by the low heating value and multiplied by the cost of the fuel, so I can compute the OPEX related to the fuel. I have computed how many carbon emission our plant produce. Here you can set which is the carbon tax. I don't know, we can put $25 per tons. So you have almost 10 million CO2 carbon tax per year. Then you have the maintenance cost that I set as a 5%, or as mentioned, you can complicate the computation by combining also the value in US dollar per kilowatt hour or megawatt hour. So we have defined which are the operating cost. And then here we have the yearly production again computed as the sum of the power output generated by our asset. In this case, I only consider one CCGT power plant, so we have the yearly production of the open cycle gas turbine multiplied by the specific cost. 18 is a bit too high, probably we are selling at 12. So we can modify these indexes and we know how much revenue we make. So after running all the analysis, we have these two charts that are the LCOE and the net present value one. I have summarized for you the value here, and I will start to show you. So if we consider a 35% yearly average efficiency with the same constant, so the same capacity factor in the same plant, we have an LCOE of 83 and a net present value of 773 million in 20 years. If you just increase, for instance, the efficiency to 36 because you're able to operate it better with some devices that can control, I don't know, the ambient temperature, for instance, you see that the LCOE become lower. And this is correct because we are consuming less fuel to generate the same capacity. So the operating cost reduces and simultaneously the net PV increase. Now I put again the same value because we want to show another impact. So you can go to the maintenance cost. You say, I can optimize the maintenance from 5% to an equivalent 4.5%. And also here, you will see that from 83, you drop to 82. You want to account for the carbon tax instead of, sorry, here I increase one decimal just to show you that now it's 4.5, not anymore 5. You want to compute a scenario in which carbon tax instead of 25 is 80, you can compute it, you calculate. So now you know the LCOE comes to 94. So you already know that if you need to provide, and this one is very important when you define scope 1 and scope 2 emission, and you are selling electricity to a third party, you need to plug in your cost the equivalent cost of the CO2 that make you ranging, if let's say case 0 and 80, from 76 to, I put again, 80 to 94. So you have $18 per megawatt hour that are the embedded cost of the fact that you need to pay the carbon tax for scope 1 emission in your plant. And typically, you don't want to pay this cost. You want that your customer pay for it. So you need to know which is the marginal cost that you pay for the carbon emission. And then you can run different scenario analysis. Here, I created the case in which you have the residual value. You can compute the revenue, the OPEX. Usually, this kind of Excel sheet are quite flexible. You can change the cost of the fuel. Imagine you pay the fuel more. You can make the same analysis here. If my fuel cost increase, which is the LCOE and which is my profitability. So you understand that if you want to come back of the investment of the year 8, you cannot sell anymore at 12, but you need maybe to sell, we increase at 20%, probably around 14 or 15. You can come back to the same ratio. So with these metrics, you can understand which are your policy of selling and purchasing assets to generate the revenue you would like to have for respecting the KPI from the financial perspective. So this is something that is a very complicated matter because it's something you need to do before starting the design of the power plant, because you need to start to consider what's happening. And we still haven't varied. I come back to the previous value of the Excel file, which is the impact of the capacity factor. Then this is one of the main problems that now OCGT and CCGT has, that they don't run so many hours in a year. So the profitability comes at year 6 with a 25%. Imagine you can start to provide scenario in which you run for 65%, you come back of the investment at the year 3. And for doing so, you need always to assess what is the best configuration and so on. So I go back to the presentation for the concluding slides. This Excel file has been adapted to this presentation, but it's what we have been really doing in Southeast Asia for a real project in which a large customer that has high intensive consumption for green electrons requirements asked us to carry out a preliminary design of a 200 megawatt, 100% fed by green ammonia CCGT power plant. And we ran all the analysis, we computed everything on a baseline that was running on methane. There was the year 2022 when I did this job in Southeast Asia, and after COVID, the prices were a bit higher, so the LCOE was coming of about $200 per kilowatt hour. And then we provide the preliminary design of all the infrastructure, so the connection to the ship, the cracking process, the compressor for the hydrogen, all the value chain from the ship to the combustion chamber of the gas turbine, and the cost of the electricity generated would have been ranging from $200 to $900 per kilowatt hour. And we could have performed this analysis only by accounting the LCOE, because at the moment there were not other alternative than using the LCOE for accounting for what the profitability of the plant could have been, because there were not other bioproducts to sell. That's why, as I mentioned before, despite the limitation, LCOE is a very powerful metric, because with simple assumption already start to drive you to the understanding of which is the price that the customer should pay for allowing you to come back of the investment. And the only question that I can leave you on this slide is, and it's the same question I make to my client there that for NDA I cannot disclose with you, was who's going to pay the premium cost of running in green ammonia in respect of CH4? And my client replied to me, I don't give a shit, sorry for the bad word, it's really what they reply me. The customer is going to pay the premium. So this is coming back to our beginning slide on the revenue. If the revenue model allows this cost, we don't really care about much LCOE, because the revenue cost will make the system profitable anyway. So for concluding, when we go for a full techno-environmental economical assessment, we need to consider mainly 3 parameters. One is the location, because every location has a different specific cost for each term. So labor cost, material, the contingency, the currency. Then there is a part related to how it's easy to connect our plant to the grid. So do we need to build the infrastructure? We don't need to build. Is the infrastructure ready to provide additional services like contingency, voltage regulation, primary control, secondary control? This is another aspect to take into account. And then there is the part of the soft cost that is the one related to how I engage with stakeholders, which is the percentage that will lend me the money, which is the cost of the land. So basically all the side part related to the power plant installation. And this regional factor has a real impact on the economics of the power plant. So for concluding, the main step that I would suggest and recommend to follow when you want to start to have a decision-making aware process for deciding if go on or not with the technology is to select, first of all, which technologies you are benchmarking and running the LCOE for both the technology. Understand which is the fuel that you're going to use in compliance with the regulation, which the procurement strategy should be, understanding which are the stakeholders that you would like to engage to maximize your profitability and reducing the risk and the exposure. Understand if the plant can also be optimally operated to supply different bioproduct, not only the electricity, but other assets that can be connected in an industrial reality in cogeneration, or if you are close by to the seaside, maybe to maximize the capacity factor to generate some desalinated water. So understand also the flexible integration of the asset into the infrastructure of the location. And then after that, you have to run the techno-economical assessment to understand which are the KPI you would like to supply and to satisfy. And only after this process, you are ready to say, hey, let's move. This is what I would like to do. So thank you very much for your attention. I am very happy to answer your question. And this is my mail address if you would like to reach it out privately. And one more time, thank you very much all for the attention, and ETN for the great opportunity to be here. And if there are any more questions about some computation, please shoot it out. I'm here.
Thank you, Stefano, for your presentation and participating at today's webinar. So I propose you raise your hand whenever you have a question or you also want to comment Stefano's presentation. You can also use the chat. Still have a few minutes before the second presentation. So we'll still have time in any case, also after the second presentation by Engie. So in case you still want to ask any questions to Stefano now or afterwards, you can still raise your hand. We'll unmute you and you will be able to talk, or you can still write on the chat, as I just mentioned before. I still thank you, Stefano. And now I would like to give the floor to Engie, to Armando and Xavier for their second presentation.
All right. Thank you, Stefano, for a very interesting topic on economics. Thanks. So today we take the second part of this presentation, being Engie. Engie is a worldwide utility producing electricity, and Laborelec, basically our company, belongs to Engie. We are the technical competence center for Engie, and we support the complete electricity value chain, thanks to ad hoc specific expertise in all type of topics related to electricity, from its generation through its transmission, distribution, use, and storage. So, of course, it's a technical topic, and it means that you need subject matter expertise in many of those. And basically, we as Laborelec bundled all those expertise under one roof. And in this respect, well, we are happy today to share a bit more what we do as far as plant profitability is concerned, but looking it through first a technical challenge and how it can benefit afterwards to the economics. As Stefano has just explained, well, basically the geography where you look at has a deep impact on your economics, and that's one of the reasons why, as Laborelec, we have also branch offices spread over the world to capture the local market specifics and translate them into, let's say, technical services to boost the profitability of our plant and troubleshoot whatever issue they have. So today we are going to guide you through, let's say, two topics. So no need to re-explain what CAPEX and OPEX are, because Stefano did a very good definition of all that. But we have opted to split a bit this presentation between CapEx and OpEx and how we can act on them to optimize the plant economics. Of course, the 30, 40 minutes we have ahead of us are not enough to be exhaustive. So we have decided to take a number of aspects where we know are generally the low-hanging fruit and where it's possible to, on a rather short time basis, optimize the cost. So I will leave the floor to my colleague Armando, which is one of our senior mechanical expert who will guide you through the CapEx section, and then I will take over for some OpEx one.
Thank you, Xavier. So let's get started. First point we will speak related to CapEx would be maintenance interval extension, and on brackets we mentioned gas turbines. Not to forget that it's mainly mean for gas turbines. So that's I didn't want to forget it. That's why I put it here. So mainly on gas turbines, the capex and the expenditures you will have on spare parts is something you know from the beginning, like from the moment you buy your assets. So all the schedule is more or less clear. So we are focusing this product on gas turbines. So first question. Why would we consider an extension? Extension on what? So on the next slides, I will explain why do we mean by extension. So in basic words, we are speaking about extending maintenance intervals, extending life of components, but why? First, let's discuss briefly that point. So we know that most of the cost of the outages are related to capital parts. And on this case, we refer to the spare parts. So if we can do a much efficient use of the life of those components, at the end, we are getting money. We're saving and reducing our expenses. So that's why we put here on the picture, because one of the things we will discuss today is the balance we propose with this methodology. So from one side, we can actually save money by extending intervals, but at the other side, there are risks that our unit may be exposed to. So that balance is something we need to take care of by the proper methodology. Additionally, other points why we would consider an extension is in today's scenario, flexibility is really valuable. So the lead time for spare parts is something that is increasing right now. It's not what it was before. Now we hear that we have to wait for a unit, for a rotor or for any big part for 18 months, for 24 months. So it's really something that needs to be managed. Again, we have bottlenecks on workforce and also on the availability of the workshops. So having the possibility to be flexible on the time where we do our maintenance, it's something that brings a lot of value on this time where we have some new constraints, not only money-wise, but also on the availability of other resources that are needed. So that's why we have to consider an extension. And additionally, just to continue here, interval extensions, maintenance interval extensions are possible, but there are risks that come with it. So we need to analyze it. We need to mitigate those risks, and that's how that is one of the things we take care of with our methodology. And one important point, if you have questions later, do not hesitate, but to have the insurer involved in the whole process is really important, is really key. That's one of the most important stakeholders on the whole process, is the one that will save the unit, will continue to ensure whether you change the maintenance planning. So it's really important to have them involved from the beginning. And in our experience, we had good results with them when they're really aware that the really actions are being taken care in order to mitigate risks in this sense of extending or modifying your maintenance schedule. So to give you a conceptual explanation of what we are doing, some examples also, but in basic words, maintenance interval extension is to have longer time between outages. This means that we have our maintenance cycle a bit longer. We run for more hours. So you can see here on the graphic what the OEM recommendation is. So you have a certain amount of
hours or years of operation in between maintenance cycles. But what we propose is to do it a bit longer. So in this case, what you can see that after doing it this repetitively, you can have one less maintenance cycle in the whole life of your unit. So this is just one very simple example. And then, for instance, we have experience on many technologies, but just to mention a few. On GT26 on Alstom's technology, we have extended intervals in between hot gas pads from 32 equivalent operating hours up to 40. So if you look in perspective, this number at the end of the life of your unit, you will avoid one outage, which is a lot of money in savings related to the time the unit will be out, the spare parts, and also the repair works. So it really has an impact. And then another way we can do some extensions. So that's another, just to show you another flexible option you can have for your maintenance schedule. So also the reconditioning cycle of parts can be deferred. So we have realized that for some components, after they finish their first cycle of operation, there is still remaining life on them. So normally the OEM recommendation would be to go for reconditioning, but we have realized that the condition, for instance, is still okay. So with minor activities like some visual inspections, NDT to discard some damages or risk, we can actually have the parts running for one additional cycle without doing the reconditioning. So at the end, all of these activities can help to have some more savings in maintenance costs. So at the end, here just to mention again some examples. So for instance, for the low pressure turbines, Series 3 and 4, we have been able to skip the reconditioning, and thus that simple activity can have savings or up to 2.5 million. So again, this is direct savings on the maintenance cost. And then another example, just to show you the things that are possible. So for major components, which maintenance cycle is not as rigid, or it's not like the hot gas pad that need to be replaced every small intervals. So even on bigger components, lifetime extension is possible. So for instance, on rotors or also on compressor section, life can be extended with the proper assessment, knowing the risk, seeing how to mitigate them. Just to give you a few, again, examples here. For instance, on a GE7FA, the rotor is supposed to live or is fair destacking after 144,000 operating hours. But we have realized that this can be extended, for instance, 152, that's one example we have done, and the savings can be up to 700,000 euros. But then another assessment had realized that we can go even further, and then the numbers start to be bigger and bigger. So these are three things that in very general words we show how to do extensions. And now I don't think we have too much time to explain how we do it, but I will show you an example so then you can easily know what we are talking about. So here we got the request from a client to do the extension, 7FA GE rotor. So again, initial life is 144 factor fire hours, and the client wanted to reach 178. The reasons, yeah, I don't remember in this case, but normally you have the possibility to align the gas turbine outage then with the steam turbine with the boiler, or to have several majors at the same time. So some efficiency is win there, and that was the request of the client. Then first step for us is to see whether this is feasible. And here is when we come out with a risk matrix, with a set of risks that needs to be studied and mitigated. And finally, we have our maintenance interval extension program, which is a set of activities that will help us to understand whether those risks we are afraid of, whether the things we understood that may happen are happening, or what is the status. So for instance, here, some visual inspections and a set of NDT were done on this rotor to mitigate identified risks. Next slide. So here, to show you a bit how the process was. So as I mentioned before, visual inspection, a set of things were identified. So we look into the rotor to see whether something was, how was the condition of it. NDT also was recommended in some sections that we know for experience on the TILs or on user conference that are actually those that may fail. So on those points, we did NDT just to see what the condition was. At the end, we are discarding any damage, any risk to see whether it is feasible or not to go for an extension. But yeah, we have strong lab capabilities. So you can see we can also destroy X work parts with a referential amount of hours just to know what is the expected condition of the material, of the microstructure at that stage of the life. So then we can get a reference to compare to see what we may expect on the life of the component we are assessing. So I will summarize this case right away. So at the end, after our visual inspection, the result is okay, no findings. The mechanical testing considered that the material was still on good condition. We checked for creep onto the microstructure. It was still comparable to a new material. So at the end, the picture we see here is a rotor that ran for 152 hours. So still 8,000 hours more than the original life. And then our conclusion is that the condition of the material is still comparable to a new one. So that this is just to show you one case that was that we succeeded to do. And then also our conclusions are based on the condition of the material and the findings, and also modeling that we are not mentioning here is that the life of this rotor can even go further, so can even go for more. But in this case, at the end, the client, for many other reasons, decided to stay there. So what can we take away to close the discussion to maintenance interval extension? So we can defer capital expenses. This methodology that we didn't have the time to explain how we do it can bring you some, can help you to reduce costs, to get flexibility, to keep your unit operating when the high revenue, when you have periods of high revenue. So you take a good opportunity, you can defer your outage when you better need it. It's important to mention that risks are there because we're extending when we're going far to what the OEM said, but with the proper methodology, with the proper inspection, with the proper experience, at the end with the proper assessment, generally in the whole condition and history, we can actually take care of those risks, which is very important. It's not just extending for whatever reason. So the risks are there, but needs to be taken care of. It's very important also to keep the stakeholders well informed. So in this case, one that we highlight are the insurers, which people may tend to think that will not like maintenance interval extension, but actually we had good experiences. When we show that the procedure is safe, is secure, that we are taking care of it, it works well. And we have real world cases working on several units, on several technologies, and also on different components. So it is possible, and that's something that can really help reduce costs. But yeah, I mean, I said already the beautiful part, but maintenance interval extension is very strong when we have units operating on base load. And now we'll jump a little bit to cycling, because it changed a little bit the rules of the game. So the evolution of the failure mechanisms is not the same when you have base load and when you have cycling. So that's something that needs to be accounted. That's something that needs to be studied and assessed to really see whether your extension is feasible or not. So I'm saying that it brings some other challenges. I'm not saying that's not possible for cycling unit. We have done extensions on unit which are actually with daily cycling, so it's possible. So I still have some few minutes before I give the word to Xavier, and now I will quickly speak about cycling just to bring it to the table, because there are costs that actually we do not see. So
when we change the operational profile of the units, the failure mechanisms and also the things we were experiencing are not going to be the same. So the things that were making your unit fail before are not the same that when the unit is actually cycling. So now there is a new trend that we have here, which is low cycle fatigue, and it's going to be really accelerated, and it's going to be present when you have your units cycling. So on the picture, we see a gas turbine, and cracking would be the way low cycle fatigue will show itself. We can see it on the capital parts, but also on different components of the rotor, and the OEMs now are understanding this and follow it to really know what the impact is. A few more words on the boilers. It's quite similar, but there are some other things that comes to the discussion, like corrosion, thermal shock. But again, low cycle fatigue will show itself in the way of cracking on many hot and thick components. That's something that may bring some other additional cost for maintenance, for repair, as unavailability and loss of reliability on the units. So just to finish with this, I'll go to steam turbine. Just one example of the things that can happen with the cycling, because we consider that the impact of this failure is really expensive. So one of the things that we have observed are cracks on the rotor, especially on the steam admission, but it can change from design to design. But that is one of the failures that at the end turns out to be really expensive. So on the picture that we see here on this example, this was actually very expensive, even more than 10 million euros in terms of unavailability and also the repair works. Actually, that's something that before was experienced after years of operation, like after 20 years of operation, but now the paradigm is changing because of cycling. So these kind of failures can be seen even after 5 years or even after 10 years of operation. There's a huge impact for the cold starts on the life of the rotor. So that's something that needs to be looked at, because the way you operate your machine will have different impact on the costing. So just to close my section, what can we do? Modeling can help you to identify when your unit can fail and where. So some other activities like NDT can be done in order to mitigate risk. So with this, I give the word to Xavier.
Well, thank you, Armando. So basically, next to the capex, now where there's obviously plenty of opportunities to improve the economics. The OPEX is also one of the topic to focus on to do the profitability of the plant, and typically one of the most underrated source of let's say loss of economical performance of plants simply reside in the proper selection of the gas turbine air filters. These are in comparison with all the other investment you need to do when you build and operate a plant. It's one of the least expensive capex, money extensive investment you need to do on a recurrent basis, but it has a huge impact on operation. The wrong filter can lead to a fast degradation of the performance of your gas turbine, which is represented on the left graph, where you see that just over a couple of months, you are losing up to 15 megawatts, which is huge in terms of loss of revenues. And this is translated also into, let's say, the technical world. It's not only about losing revenues, but it's also increased cost, because if you need to achieve, in some instances, the same power output, you have to burn more gas. So it further degrades your economical performance. And I'm not even speaking here about the downsides of having bad filters, which basically results in having a lot of dirt, contaminant, even corrosive contaminant entering into your machine, and which ultimately degrades faster than expected and can even cause some dramatic failure of it with extended long time for repair, shutdown, plus cost for procurement of new parts. So it's really something to look at into more details. So in order to tackle this issue, we have developed a tool which aims at basically optimizing the selection of the filter for the environment, which is specific to the site, and which is based on the total cost of ownership approach. So there, the idea is to translate into money all the technical commercial parameters of the plant to figure out whether it's relevant or not to change the current filtration system in place at the plant. So by combining the information and the data on the technology you operate at the site, plus what has been already installed in terms of filter and all, basically your plant is behaving in this with that system, plus clubbing it with a forecast of operation, because okay, we know it was in the past, but we have also to see how it's going to change over the future. And as probably many of you knows, it's far from being stable, the electrical scene. So you have to take some scenarios and make some forecasts to see how profitability will change and your cost as well. So all that need to be integrated into that model to come up with the total cost of ownership of your current filtration system and the plant itself. So once this is done, then using some, let's say, magics, which is about processing data, plus having the knowledge of the different filtration system available off the shelf, you can reconcile all those aspects into the model to figure out whether or not there is opportunity for you to change and how much it will be. Our experience with F-class gas turbine tells us that when you upgrade your filtration system from what we call the F9 level, which is nowadays, I would say, a kind of state of the art, or at least initial filtration grade you can expect in plant, and moving it up to E10, then you can realize savings ranging typically between 200,000 and 400,000 euros per unit per year. And so you see there's already quite significant savings to be done there. Just a remark at that stage, it's not because you say, okay, I will go FF9 right now and I will move to E10 filtration class that I'm going to make savings. You have to compare, because on the market you can find filter labeled E10 performance, E10 filtration class, but that are basically not behaving as good as the alternatives. So you really have to compare each and every solution available on the market to choose the right one, which is adequate for your environment and your, let's say, forecast of operation. So with the filter, that was all what I wanted to explain right now, because for the sake of time, we have to move on a bit. But another aspect I just would like to also bring some awareness on is about the startups. So the plant nowadays have to operate in a more and more challenging environment, where while they're used in the past to be, just started once a week or once a month, nowadays certain plants need to start and stop like twice a day, making the startup, let's say, a key factor in order to capture the opportunities that are on the market. So it means that in order to be profitable and capture those island of high profitability on the market, you need your plant to be able to start in a reliable and efficient way. It means that you need to also understand what are your startup costs. So basically, a startup average cost is ranging between 5,000 and 15,000 euros per start, generally mostly associated with degradation of your capex, which Armando has just explained. But in order to really, let's say, improve the startups, if you are, let's say, if the performance of the startup is not optimal, you really need to dig into, let's say, the control logic which drive how the startup is done, and This will enable you to look into, let's say, this logic in order to translate the different startup strategy you'd like to take, or how you manage, let's say, how fast the start is done and what's the impact, for instance, on the steam turbine. Plus other opportunities that are well known in the world of flexibilization of plants. So all that you need to really study, know what you want to achieve, and then let's say translate it into changing the logic and the way you are going to control your plant moving forward. So these are all essential steps to be taken in a controlled way in order to let's say boost the profitability of your plant, but it means you need to study. Typically, and I forgot to mention it, a startup, the metrics typically used to assess their performance is generally how long it takes for the plant to be available, full capacity for the grid. What's the gas consumption you had to reach that level? And last but not least, also, what was the electricity that you have been using via your to feed your auxiliaries to reach that level? So these are the three metrics typically you need to analyze and then see whether each startup you are undertaking is repetitive, and investigate in case of deviation. So I will now conclude this webinar after having reviewed the macroeconomics, the capex, opex, and how to optimize them. And I would say the word would be that dare to be opportunistic. If you want to really reach a high profitable plant, well, basically you really need to understand those macroeconomics and also how you can leverage at best all the usual conservative rule that have been embedded in your plant at the design stage. And this can be achieved through looking into in detail to your capex, opex, but this has to be done in a way that does not introduce exaggerated new risk level, because otherwise it can even degrade your economical and financial performance in case something goes wrong. So in power plant, there are different opportunities which you can leverage. Of course, you are bound by different type of contract with EPC, with OEM, whoever. So you have to look also into your contract where you have some freedom to play on, and starting from there, see what are the action to improve, or extend the lifetime of some gas turbine component or the rotor of your gas turbine. You can also leverage basically when the contract expires. If it's just a time basis, you may want to wait few years, and then really start at that point in time your program to improve profitability. Of course, the local team has also to be really mindful on the actual performance of the plants, and really being really knowledgeable of the process to identify where opportunities are, where it's possible to improve, where we see deviation and lack of recurrency. And basically, all that generally require time and investment in order to investigate. And in some cases, like I explained for the filters, you can have also very fast return on investment, generally a couple of months, just by taking the adequate choice in the different areas of the plant, like the filters. And of course, it's important at any stage when you are trying to undertake a risky operation for your plant to involve your insurers as well as the stakeholders, so you have their buy-in, and together with the different experts you may call upon, you can build, let's say, strong business and technical case to defend, let's say, the initiative you take to improve the profitability of the plant. So that's the end of our presentation. So now probably we still have quite some time to grasp some questions, reply to them. So feel free to post them on the chat or even activate the mic. Nicolo, I don't know if it's possible. So we're there to answer any of your query.
Thank you, Xavier, and thank you, Armando, for your detailed presentation. So yes, we still have some minutes. I just enabled the mics for all the participants, just for you to know that you are also free to complete a Slido that we just shared with you in the meeting chat, where you can provide feedback to the webinars provided by ETN. Any feedback you may provide is very useful so that we can improve also our services and products for the future. So you're very invited to complete this webinar feedback questionnaires. In the meantime, we open the question and answers session for both presentations again. So if you have any questions, please unmute yourself or raise your hand or write in the chat. So please, those is yours. Alexander, please.
Hi, thank you. Thanks for the presentation. I just wanted to ask a question on sort of how you assess the value of metrics like startup times, for example. Like, let's say how do you assess what the value of reducing your startup time from a 90-minute cold start to an 85-minute? How do you assess that value, not just in reduced fuel you might have to burn to get on load, but also how likely that will be that you'll even be put on load?
So basically, the way we capture or we evaluate the value of a stat is basically the approach is to build a database of what your plant is supposed to be delivering, or in terms of performance for cold, warm, hot starts. So basically, when at the very early stage of your plan, we commission it, you get their first reference, and then either the local team or any consultant you may hire, they are going to analyze, do like a look back analysis on the plant. And you can run a number of algorithms on the data which are present in your historian, and computing basically the three main metrics I shared before, being the time duration, the duration, the gas, and the electricity. So you can associate a cost with all that, and so basically it brings you to let's say quite some level of detail for each and every start to see where you have been, like compared to the other start or the average or min max value, where you have been faster or slower. And so when you do run the comparison, then okay, say you can reflect on, okay, this one has been faster, so normally better for me. And what have we done different that time, or what were the conditions at that time which enabled to have this stuff done in such an efficient way and minimizing our internal cost. And so it's by building up this return of experience, then you can really refine your process and the way you control your units to achieve optimal performance.
Thank you for your question, Alexander, and thank you for the response, Javier. We still have some time. In case you have any questions, please feel free to speak.
Of course, if any of you sleep on it and tomorrow morning got a brilliant question to ask, of course, feel free to reach over the email address that were given in the presentation today. we'd be more than happy to answer them offline if nothing pops up right now.
So if you have any questions as such, either to Stefano, Armando, or Javier, please let us know, write us an email, and we'll put in touch with the presenters. So with this, we are approaching the end of today's webinar. For those who are going to participate at the International Gas Turbine Conference in about 2 weeks' time from now, the 14 and 15 October, here in Brussels, we will also have the second episode of this series on the profitability of thermal assets. This time will not be online, rather it will be in person with a keynote speech by Montel, participating in a keynote speech in a panel on the market overview at the global level on gas turbine markets. And there will be other webinars as well on CRM markets, adequacy reports, comparison among different European countries with a final summary or wrap-up session at the annual general meeting in March 2026. So with this, we look forward to see you online and in person very soon. Please do not forget to register for our IGTC, and we wish you a good day and a good continuation.